Hi everyone. Today we're going to talk about polar graphs in calculus. But before we do that, let's first go ahead and review what we remember from polar graphing back in trig. So if we're taking a look at this opener here, it says Alice is standing at the origin and walks at a direction angle of 30 degrees for a total distance of 4 units. Determine her destination point and sketch it accurately as you can on the graph on the right. So what we're talking about here, right, is starting from the origin, making a 30-degree angle. And so, we talked about direction angles when we talked about vectors. It's kind of the same idea here, right? And we're going to walk in that direction for a distance of 4 units, okay? And so looking at an ordered pair like this in terms of how far did we walk from the origin and what angle are we making, so think of it like a unit circle angle, right? That is what we were talking about when we were talking about a point in polar coordinates, which is r comma theta. And for this specific point, it would be 4 comma 30 degrees. Okay, right? This point right here, right, is written in polar coordinates. So we're going to go ahead and write that in here as well. R comma theta is 4 comma 30 degrees. Now, one mistake that students make with polar is they think it's some totally crazy type of system, especially when you start looking at polar graphs, right? Which don't look like graphs that you're used to seeing. We'll come back to this in a moment. But really, it is just another way of talking about the exact same types of ordered pairs that you do in Cartesian coordinates, right? So this r comma theta, which I've just highlighted here, right, 4 comma 30 degrees, it has a corresponding x and y coordinate, right? Because I can still look at this graph and I can go, okay, right, how many units over are we from the origin horizontally? That's my x. How many units up are we vertically from the origin, right? That's my y. I can still talk about this exact same ordered pair in terms of x and y, right? Just like how we have in the past. And if we do that for this specific point, it would be 2 root 3 comma 2. Now, we'll talk in a moment about how to actually come up with that x and y. So if you don't remember how to do that right now, that's okay. A little SOHCAHTOA stuff we'll come back to. Okay, but the main idea here is polar graphing is just another way to talk about the same XY Cartesian coordinates. We're just representing them using a completely different set of data rather than the horizontal and the vertical from the origin, right? Instead, it's what is the direct distance from the origin, that's my radius, and then what is like the unit circle angle or the direction angle that we are making with the positive half of the x-axis. That's the theta. Okay, so when we have polar points and polar equations, though, we don't typically look at them, though, on our x comma y, our rectangular coordinate system, our Cartesian coordinate system, whatever you want to call that, right? Polar graphing is typically done with these concentric circles, okay? So the first thing I did here on this graph is I went ahead and labeled from the origin what the radius of each concentric circle is. And this is basically working as my x-axis, right? So, this point in the center, the polar origin, right, is a circle with a radius of 0, right? This is a circle with a radius of 1, circle with a radius of 2, circle with a radius of 3, etc., right? And then you'll also notice that I've labeled the negative values here as well, right? Can a circle have a radius of -8? Technically, no, but in polar graphing, when I have a point that has a negative r value, right, that just means I'm going to start on the left half of where we would normally consider the x-axis to be. Okay, so let's go ahead and practice some polar graphing here real quick. So I have point T here labeled as 3 comma 120 degrees. And so the way I like to think of these graphs is I like to kind of draw out a little path or a trail to get to that point. So starting from the polar origin, I'm going to do little dots here to show you my trail. I'm going to go out to the circle with a radius of 3, and now I'm going to make a unit circle angle that is 120 degrees. And so on these polar graphs, it's nice because you'll see the angles are labeled here. So I want to get to 120 degrees. So from my circle with a radius of 3, right, I like to do these little dots to show what my path is, right? This point right here is point T, okay? So you don't need to have all of these tiny little blue dots that I drew, right? It's just to kind of show you how are we getting to this spot, right? And so again, I like to kind of show you my path when I do this, okay? Let's use for a couple more points. So point P is 6 comma negative pi over 4. So from the origin, I will go out to a circle with a radius of 6. And now a negative unit circle angle means that we are going to go clockwise. So I'm going to go down, right? And so this is 30 degrees. That's pi over 6, right? Pi over 4 is 45. So that's going to be in the middle. So that's going to be like about right there. That is point P. Okay. And then we have point Q, which is negative 5 comma pi over 3. So from the origin, I'm going to go left to the circle with a radius of quote unquote negative 5. Of course, we know a circle can't have a negative radius. And now this part gets a little tricky. If it's a unit circle angle of positive pi over 3, then I need to go ahead and rotate counterclockwise still. So I need to go pi over 3. That would get me to right there is point Q. Okay. So hopefully you have the idea here of how we can graph point and polar. Okay. One other thing I'd like to do here is show you that we can represent a polar point in actually infinitely many ways. So thinking about this point T, right, which had a radius of 3 and a unit circle angle of 120 degrees, right? So, we graphed that first. Here's point T. So I went out to a circle with a radius of 3, and I generated a positive 120 degree angle. But what if I had made a negative angle instead? I still could have gotten to that exact same spot. So another way of representing point T is 3 comma negative 240 degrees. And now both of those points are assuming that I'm going to the right from the polar origin, that I am choosing to start where I have my positive radius values. What if I have a negative radius value? What if from 0 I would go out to the left first to negative 3, and now I could make a positive angle to get to point T up there, right? And that would be negative 3 for my radius, comma, 300 degrees. Okay, and now same thing. What if I had gone from the polar origin to the left to negative 3 and made a negative angle? So remember, negative angles are clockwise. So from origin, go out to negative 3, so I'm right here, and then a clockwise 60 degree angle, and so that would be a radius of negative 3 and then negative 60 degrees. And now just one thing, based on my work so far, right? I guess those two had radians down there, but what I was going to say is you don't have to write stuff in degrees if you don't want. You can do stuff in radians and polar, it doesn't matter. Okay? But technically, I can represent point T in these 4 ways, and actually I can represent point T in infinitely many ways because I could then take the coterminals of these angles. And some of these are already coterminals, right? 120 and negative 240 are coterminals. I could take negative 240 and subtract 360, right? And get that point T is 3 comma negative 600 degrees. That would also work as a way of getting to point T. So that's an interesting fact with polar coordinates, that there's infinitely many ways to represent the same ordered pair, right? You can't do that with Cartesian coordinates, right? If I'm talking about this point right here, there is only one distance horizontally and vertically to get to that point. There's only one x and y. Could I write x and y in different ways? Yes, right? But that's literally just writing an equivalent form rather than in polar, I'm talking about a completely new path to get to the same point, okay? All right, so let's keep going. So a little more talking about the similarities between polar and Cartesian coordinates. Okay, so I have the same kind of picture from the top of the previous page here, right? So I can look at any point, any ordered pair, x comma y, in terms of the horizontal and vertical, or in terms of the radius and the direction angle, the unit circle angle. Okay, and so because I can do it this way, I can create a little right triangle here, and now I can do a whole bunch of trig things that you've all seen before. So the first thing I can do, Pythagorean theorem, right? R squared is going to be x squared plus y squared. I could then go ahead and solve for r. R has to be the square root of x squared plus y squared. And now I can just do a whole bunch of SOHCAHTOA. Okay, so I can set up that the tangent of theta is y over x. This is a nice formula to remember because this is one where if you have the Cartesian coordinates, the x and y, you could then use this to find what theta is. Okay, so that's a good one to know. And similar with the one above it, the r equals square root of x squared plus y squared. But we can keep going with some SOHCAHTOA. Sine of theta would be y over r, and therefore we could write y as r sine of theta. We can do the same thing with cosine. Cosine of theta is x over r, therefore x is r cosine of theta. And now we can use these last ones right here to now convert back and forth between a Cartesian equation or a rectangular equation into a polar equation. So let's take a look at that with example 1. Convert from rectangular to polar, y equals x minus 3. Well, what did we just say y and x equaled? Y is r sine of theta, x is r cosine of theta. We can just go ahead and plug those in directly, and now I have an equation with just r's and thetas in it. And so when we want a polar equation, right, we are going to isolate the r value. So in this case, I have two r's. So I'm going to go ahead and bring them to one side. And so I have just the negative 3 on the right. And now I can go ahead and factor the r from both of those terms. So I get r quantity sine of theta minus cosine theta equals negative 3. And then the last step, I can just go ahead and divide. And so the line y equals x minus 3, written in polar form, is r equals negative 3 over sine theta minus cosine theta. Now, if you're looking at this, right, I hope you agree with me, this looks pretty complicated, right? And that's because, one of the basic things that you can graph in rectangular form, Cartesian form, whatever you want to call it, are lines, horizontal lines, vertical lines, lines with a slope, right? These are the most basic things that you learn how to graph. That is not the case in polar, right? So a line in polar looks kind of complicated, okay? Okay, let's go the other way now, right? Convert from polar to rectangular form in example 2. So you're going to see here, I went ahead and helped us out here. R over 1 equals 2 over 1 minus sine of theta. So we're going to go ahead and cross multiply here because my goal here is to get r sine of theta and r cosine of theta so that I can replace them with x's and y's. Okay, so that's why I want to start off by cross multiplying. And so I'm going to do r times the quantity 1 minus sine of theta, and then 2 times 1 is, of course, 2. Let's go ahead and distribute. And so I get r minus r sine of theta equals 2. And now r sine of theta I know is equal to y. And then r I know is equal to the square root of x squared plus y squared. Okay, now converting to rectangular form can be a bit tricky because people are going to assume that, oh, we have to solve for y to write the final answer. Not necessarily, not when you have x squareds and y squareds and a y, because Anytime you have, not anytime, but in this case, right, this is actually going to be a type of conic section. And so which one? Let's go ahead and find out. I'm going to start off by adding the y to the other side. And so now the square root is by itself. And so let's go ahead now and get rid of the square root by squaring both sides. Now on the left-hand side, the square root and square will cancel. On the right-hand side, I'm going to have to FOIL. And now I can also go ahead and cancel out the y squareds on each side. And so if I'm looking at this, I have a y to the first, and I have an x squared on the other side. And hopefully now you can recognize that this is actually a parabola. And so because I know it's a parabola now I can go, okay, let's get the y by itself. So we're going to go ahead and subtract 4 and divide by 4. And so we get x squared minus 4 all over 4 equals y. Okay. Okay, let's do a little bit of graphing, and then we will talk about some calculus. So example 3, graph the following polar equation. R equals theta over 2. So again, polar equations are going to be r equals something, right? Now in a rare case, sometimes it'll be r squared equals something, but we'll review that on another day. Let's go ahead and talk about graphing. Now, the nice thing with graphing is we just treat it like a function, right? We can plug in theta values and get r values. So I have a few different theta values here. Let's go ahead and plug them in and we'll get the corresponding r value. So when theta is 0, r is going to be 0 as well. When theta is pi over 2, r is going to be pi over 4. Now, in terms of graphing, it's kind of nice to know what some of these numbers are as decimals. And so a quick way to figuring out stuff like this is, you know what pi is, right? Pi is approximately 3.14. Cut that in half, pi over 2 is approximately 1.57. We can say about 1.6 for graphing purposes. So pi over 4, cut that in half. We know is in the neighborhood of 0.8, right? Is anyone going to be able to tell that your graph isn't 0.8 when it should be 0.7 something, right? It's not that big of a deal, okay? Let's keep going. All right, pi. Cut that in half, pi over 2, approximately 1.6. 3 pi over 2, cut that in half. We get 3 pi over 4, which you can, take your pi over 4, multiply it by 3-ish to get around there. And then 2 pi cut in half is pi, right? And so we know pi is approximately 3.14. We'll just say about 3.1 for graphing purposes, okay? So what is this going to look like, right? So let's go ahead and basically play connect the dots, okay? And so here's my point at theta is 0, right? And now this part is probably the trickiest part of the graph, right? Because we didn't plug in any values between 0 and pi over 2, right? And so most people, I think, would see this and go, oh, shouldn't the graph be going straight up, right? Playing connect the dots, right? Not exactly, right? Because we know we are generating thetas as we go around the unit circle, right? This graph actually works its way up, okay? And so we work our way out, right, to pi, where the r was pi over 2, right, to 3 pi over 2, where the r is 3 pi over 4. And so again, if you're not sure how we're getting these, 3 pi over 4 is 2.3, right? So the way I actually plot the point is from the origin, right? 2.3 is about there, and then we rotate around, right? And we end up there. Sorry, I was too far out. I was over here. I should have been here. Okay. And then at 2 pi, right, working our way all the way back around, we have an r value of pi. Okay. So anytime you have like an r equals theta, or in this case, like r equals theta over 2, something like that, right, you're going to get this spiral graph, which you may not have seen before, but that's a good one to know in terms of what the graph looks like. Okay. Okay, let's keep going. So example 4. Now we're going to talk a little bit of calculus, okay? Find the equation of the tangent line to the curve r of theta equals sine of 6 theta when theta is pi over 4. So sine of 6 theta, we'll talk about these kinds of equations later on and what they look like graphically. But before we do any of that, let's just go back to Calc A for a second, right? We are trying to find a tangent line. How do I find the equation of a tangent line? You've done this for semesters now, right? We need a point on the curve. Now, we always do it in Cartesian coordinates, right? X comma y, rectangular coordinates, whatever you want to call it. What else do I need? I need the slope of that line. That slope is a derivative, dy over dx, right? So everything we've done with calculus in terms of this type of question, looking for a tangent line, we always do in terms of the rectangular form or the Cartesian form, whatever you want to call it, okay? I don't have that option here, right? R equals sine of 6 theta, right? I could try to use some trig identities and break down sine of 6 theta until hopefully eventually I get sine of theta. Then I can go ahead and, try to get it times an R somehow. That seems like a heck of a lot of work. So what we're going to do is we're going to do something else we've done in this chapter, right? Which is we're going to take our polar equation and we're going to turn it into a parametric equation. Now, how can I do that? Well, by using the formulas that we just scrolled up and looked at, right? We have a parametric equation for x already, right? X is r times the cosine of theta, y is r times sine of theta. And in this question, we know that r is sine of 6 theta. So let's go ahead and substitute that in. And so we would get that x is equal to the sine of 6 theta times cosine of theta, and y is the sine of 6 theta times the sine of theta, right? And now I can treat this like I would when we did parametric equations and the calculus work we did there, but instead of having x of t, y of t, I have x as a function of theta and y as a function of theta. So how did we find the slope dy dx when we had parametric equations? We would find each of these derivatives separately and then divide, right? So that's exactly what we're going to do. Okay, let's go ahead and find dy d theta and dx d theta. Okay, and so finding those, right? Now, the tricky part with these questions, really, you just have to remember that the derivative of something like this, r times cosine, r times sine, you're going to have to do the product rule. Okay, so let's go ahead and do that here. So sine of 6 theta times the derivative of cosine of theta. I'm sorry. I'm doing the y first. Sorry, I confused myself. Here we go. Sine of 6 theta times the derivative of sine is cosine. And then I'm going to have sine of theta times the derivative of sine of 6 theta, right? So I have to do chain rule. So I get 6 cosine 6 theta, okay? And then dx d theta, so very similar work, right? I have sine of 6 theta times the derivative of cosine is negative sine, plus cosine of theta times the derivative of sine of 6 theta, which we already did from above, we know is 6 cosine 6 theta. Okay, so here's my two derivatives, right, with from doing the product rule. Now let's go ahead and take these and divide, right? And so we know that if I want dy dx, I would take dy d theta, divide it by dx d theta. But now, to help ourselves out here, remember that we're trying to do this at one specific theta value that the question gave us, pi over 4. Okay, and so the nice thing here, we can help ourselves out here a little bit, right, is what is the cosine of 6 times pi over 4? Well, 6 times pi over 4 is going to be 3 pi over 2, and very conveniently, the cosine of 3 pi over 2 is 0, which means that all of this is going to drop out, right? This whole sum, right, the second part of each of these derivatives is going to drop out when I plug in theta equals pi over 4. Okay, so again, we're doing this derivative specifically at theta equals pi over 4. And so I'm just going to, again, plug it into the first part of each of these, right? Because, again, cosine of 6 pi over 4 is 3 pi over 2. That's all 0. So I'm going to ignore it. Plug in pi over 4 into each of those. I get sine of 3 pi over 2 on both of these parts. Sine of 3 pi over 2 is -1. Cosine of pi over 4 is root 2 over 2. Negative sine of pi over 4 is going to be negative root 2 over 2. And so this whole thing is going to simplify to being -1. And so I highlighted that in orange because that is my answer for the slope of the tangent line to this polar curve. That is my dy dx value at, again, specifically, theta equals pi over 4. And so what's the other thing I need to find a tangent line? I need a point. Again, I specifically want the point, the ordered pair, x comma y, when theta is equal to pi over 4. And so conveniently for us, we already know what x and y are equal to, right? So we can just go ahead and plug in pi over 4 into each of those. And so x is going to be sine of 6 pi over 4 is, again, 3 pi over 2 times the cosine of pi over 4. So again, sine of 3 pi over 2 is -1. Cosine of pi over 4 is root 2 over 2. And so I get negative root 2 over 2. There's the x coordinate of my point. Let's do the same thing for the y, right? We're going to get sine of 3 pi over 2 times sine of pi over 4. And that is going to, again, give us negative root 2 over 2. And so I have everything I need now to write the equation of the tangent line. I have found the x and y that make up the point. I have found the slope. So the last thing to do is just point slope form. So y minus y1, so y plus root 2 over 2 equals m, my slope -1, times x minus x1, so minus negative root 2 over 2. Okay, so that one was a doozy. Okay, but now we could, take a question like this, right? We found dy dx, right? Theoretically, we could also find the second derivative, although doing two product rules inside of a quotient rule, right, would not be fun. Or sorry, two product rules for the numerator, two product rules for the denominator. All of that in a quotient rule would not be fun for a second derivative, but it is doable. Okay, last example, example 6. Find the area enclosed by the curve r of theta equals 3 from 0 to 2 pi. So r of theta equals 3, right? Notice how in this equation there is no theta on the other side of the equal sign. So basically this is just r equals 3. And anytime you have a polar equation that is r equals a number, that is a circle. Okay, so this is actually a real fancy question here because all it's really asking is what's the area of a circle with a radius of 3. Now, you guys could do that in your sleep, but we're still going to do this in using some calculus. Okay, so let's go ahead and start off with a picture. Okay, so I have a circle here, and what I've kind of highlighted here is this little kind of like wedge or pizza slice or kind of like, Pac-Man's mouth, right? That's open here. And if you remember from geometry, that is called a sector, okay? And so what is the area of a sector formula in radians? Now, you might remember it in degrees, but you did learn this in radians in trig, right? It is 1/2 r squared theta, okay? So when I want the area enclosed, when I want the area enclosed by a polar equation, right, I am going to take the integral of the sector area formula. I am going to integrate from a to b of 1/2 r squared, and because theta is changing as I go through whatever r equation I have, the theta becomes the d theta. Okay, so I'm going to go ahead and apply that to this question, right? So the area is going to be the integral from 0 to 2 pi of 1/2 r squared, and now we know that r is 3, right, times d theta, okay? And now we're just going to go ahead and evaluate this. So 3 squared, right, is 9, right? Over 2, all of that is a constant, so I'm just going to take out a 9/2. And so I'm integrating just, you can put a 1 here if you want, but you're just integrating d theta. And so I'm going to go ahead and get 9/2 times theta from 0 to 2 pi. And so we can go ahead and plug those in, right? We get 9/2 times the quantity of 2 pi minus 0. And so the 2's will cancel and we get 9 pi. Okay, so again, could we have just done pi r squared? Absolutely, right? But this just goes to show you that this formula will work now, right, for any type of polar equation we have. So we're going to do a lot more of this specifically in the future. Okay, all right, thanks folks, and I'll see you next time. Bye.